In this video, we'll take a look at an example of magnetic force on a charged particle. In this example, we have a proton. A proton is moving at an angle of 23 degrees with respect to the direction of a magnetic field that has a strength of 2.60 milliteslas. And at that point, it experiences a magnetic force of 6.50 times 10 to the negative 17 newtons. What we want to do is we want to calculate the proton speed. We know it's traveling, but we don't know what speed it's traveling at. We know its angle with respect to the magnetic field, but we don't know an exact direction in any Cartesian coordinate system of the velocity. We just know its relative direction to the magnetic field. So we also want to be able to determine its kinetic energy, and we'll do that in electron volts. And we're going to make the assumption that the only force on the electron, in this case it's not an electron, is it? The only force on the proton is magnetic force. Then we want to know what is the acceleration. So we'll develop our problem, determine what are our givens, what we want to find, and what theories we need. And of course we'll draw a diagram. So we're given the fact that we have a proton. We know the charge of a proton. We know phi, that phi is representative of this angle, right? That's that angle, short angle between the velocity and the magnetic field. We don't know the exact direction, so we just have them represented relative to each other. We don't have any coordinate system set up. And we know our magnetic field, and we know the magnetic force. So we want to find the speed, which is the magnitude of the velocity. We want to find the kinetic energy, and we want to find the magnitude of the acceleration. So our theory we can use to find the magnitude of the velocity is we can use just the magnitude of the force for a magnetic field. That's the charge of the moving particle times the speed of the moving particle, the magnetic field within which, the magnetic field strength within which it's moving, and the sine of that angle between the velocity and the magnetic field, this angle here. If we want to find the kinetic energy, well, what we also need to know then is what is this Q? Q, that's the charge of the proton. So our charge of the proton, that's our elementary charge. We know that to be 1.602 times 10 to the negative 19 coulomb. For kinetic energy, that's our 1/2 mv squared. So if we find our velocity in part A, we could use that here for the kinetic energy. That mass there is the mass of what? That's the mass of the proton, so we'll need that figure 1.67 times 10 to the negative 27 kilograms. And then for our acceleration, we know acceleration is the sum of the forces divided by the mass. In this case, we were told that the only force on the particle we could assume was the magnetic force. When we're summing forces, we must remember we have to sum the force vectors. So this problem is simplified if we only have one force. So our solution here for each of the A, B, and C, we can solve then for velocity to rewrite our equations from theory, solving for the speed, the magnitude of the velocity. We have the force, we have the charge, we have the magnetic field, and the sine of the angle, so we can basically plug in our givens to get this answer. For our kinetic energy, we can use the velocity from part A. If we wanted to start from all of our givens, that velocity we could represent as what we have for part A. And similarly, for the sum of the forces, we said if the only force is the magnetic force, then we don't need to know the direction in order to find the magnitude of the acceleration. So for part A, we can plug in using our SI units, and we solve to 4 significant digits, 3.999 times 10 to the 5th, and then we'll round that to 3 significant digits because that's our givens have 3 significant digits, so we'll use proper significant digits for our answer. If we want to use that velocity to find the kinetic energy, we want to make sure to use one extra significant digit. So when we plug in for velocity in part B, we'll use our 3.99 times 10 to the fifth instead of 4.00, and we'll square that. And we can solve for that in joules, but we are asked for electron volts, and we know that there's 1.602 times 10 to the negative 19. That's our elementary charge, joules per electron volt, and we get 835 electron volts. And lastly, we can solve for our acceleration. We see that really that's quite a large acceleration. 3.89 times 10 to the 10th meters per second squared. And if we compare it to our force is on the order of 10 to the negative 17 newtons. So the reason for such a large acceleration, of course, is that our proton has such a small mass. So such a small mass, even if given just a force on the order of 10 to the negative 17 newton, that proton will accelerate quite a bit. So what will be the direction of that acceleration? Of course, the direction of that acceleration, since the charge is positive, will be in the same direction as the force itself, but our force is perpendicular to both the velocity and the magnetic field. Because our theory, we were just asked for the magnitude, but the direction of our force, FB, that's our charge times our V cross B. So if we use our right-hand rule here, we point our fingers in the direction of our velocity and curl them, our right-hand fingers in the direction of the velocity, curl in the direction of the magnetic field. Our thumb is going to point inward, so we can write that our magnetic field is going into the page, our magnetic force, FB, is going into the page, and so this moving proton is going to do just that. It's going to be accelerated into the page. The magnitude of our velocity will not change. It's our speed, V, will not be changed by the force. Only the direction of the velocity will be changed. The kinetic energy that we solve for will not be changed by the force. And in fact, the magnetic field does not do work on the charged particle. If we use our work energy theorem, work is equal to the change in kinetic energy. So the magnetic field not doing any work, we end up here with a centripetal force, and only the direction of the velocity is changed. So we'll look at another example in this module of how to solve for the magnetic force and the magnetic field in vector notation as opposed to just the magnitude.